Hopefully I can edit this. If you're seeing this right now, Professor Gardner, I did not figure out how to. Yeah, here's my setup. I'm just gonna put myself in the corner right there. So I'm gonna do like a split screen. On the left right here is like my exam corrections, and on the right here is my original exam. So I'll be like talking about each question and kind of like doing this how I do my screencasts for the homework, where I like kind of like write on the screen. So if you like absolutely hate this setup, I won't do it again. Right, so starting off with the first question, I know I only got like one part of it wrong, and it was pretty obvious. On the original test, I put area, that Bernoulli is an energy equation derived from balance per unit area. I got confused with force per unit area being pressure. Quite honestly, I was already panicking for this exam, so I just changed up the mass on here. But yeah, Bernoulli is an energy equation per unit mass. And then the other questions I got correct, but I added them more, being that if the equation applies to a fluid flowing in and out of pipes of a heat exchanger, it would not apply for the extended Bernoulli equation, because if that equation assumes that the system is adiabatic, and if you're having heat going into the system, not adiabatic. And then what the work non-flow term over with respect to mass is, it represents work being done in the system or being extracted from the system, like through a pump or turbine. And for the extended Bernoulli equation, we don't really have that. You could get like the energy Bernoulli equation. So yeah, got that right originally, but just wanted to go over that. Yeah, second part, I got half right. What I got wrong was this one right here, that the purpose of the manometer is to measure the gauge pressure in the pipeline. It's not, it's to measure the pressure difference using just like the mercury difference. So it'll be like different levels on either side. There's usually going to be like um, a pressure drop on the other side, because like the orifice meter has like a very tiny part, and like the decrease in diameter, you're going to get an increase in velocity. And then that can just be used to measure the flow rate. I at least knew that. But yeah, so pressure difference, that's what I changed. And then for question 3, yeah, let's go on this side. Yeah, so the first part I got right. I said it would be the same if the barrel was originally also floating in the pool, because it's just using like Archimedes' law, it's just going to be an equal amount of like water displaced. But I got wrong on the second part. If the barrel was originally resting fully submerged on the bottom of the pool, it will rise when like put on the raft. This is because if the barrel was like stuck on the bottom of the pool, there's going to be a normal force from the bottom of the pool supporting the weight of the barrel. So really only what's like displacing the water is the volume of the barrel. So once it like gets placed on top of the raft, you're going to get the full like weight force, and that will equal like the buoyant force, and then also the weight of the water displaced, according to Archimedes' law. And I didn't really like state that clearly in my original, so I wrote this like long paragraph essentially stating that. But yeah, read it if you like. It's more for me. All right. So question 4. I believe I got like half a blank on that, and I know like this was correct. Um, so I'll just like move on to the pressure stuff right away. Um, I said P2 is greater than PM, because PM is right here and P2 is right here. You're already going to have like the pressure inside there, and yeah, it's just going to be less than the atmosphere. If P2 were less than the atmospheric pressure, it would be like kind of stuck enough. That's not happening in a shower. I hope not. You have to get a plumber done. Then P3 is going to be greater than P2, since P3 is at a lower height. Yeah, P3 is like right here. So yeah, originally I got that wrong. All right, so question 5, I got 0 points on, justifiably, on the original. I just didn't know what to do with it at all. So, I just really thought about it hard, um, for this and spent probably too long on this. But yeah, for defining like the mass flow rate, you just have like the general base equation, which is rho cross section of area times velocity, and those are like given to you in here. Thank goodness, or else I wouldn't know what to do. Um, so oh yeah, here's 8. Yeah, so you can just base it off of there, and then you can get the mass flow rate. And then it gets more complicated for the momentum balance. So you're gonna have like the N minus L plus Gen equals accumulation and all that for like the mass balance and or momentum balance really. Um, and so you're not really having anything going in. You're just having a bunch of like mass and momentum leaving. Um, so for the out, you're going to have like the rate of the mass flow rate um going out, and then the velocity of the gas. You can get like the momentum going out for that. And I made mass flow rate negative because the gas is being expelled like down, and then the rocket is like hopefully moving up. And then for forces, there's like 3 things going on. There's going to be the drag force, which is like um negative k times velocity squared, or like velocity of the rocket squared, which is like relative, and then relative to the surroundings, I believe. No, it's just like the velocity of the rocket. I was thinking of the V gas. Yeah, then the pressure force per area, and then the gravity. So here's the drag with like respect to air, because air is like getting thinner as the rocket goes up through the atmosphere. And then pressure force per area, that's with like the gauge pressure minus the ambient pressure, because like the ambient pressure is going to get less and less as the rocket goes up. Over again like the area and through which the gas is escaping. And then gravity is just going to be gravity times the mass equation. It's just like mass as a function of time, because like it's decreasing over time. Yeah, and I wrote like likely PM is like less than a gauge, because like so you're gonna go to space. There's no atmosphere over there. Then for accumulation, you are losing mass relative to velocity. Um, yeah, and so that also like decreases the momentum because you have less mass over time. And then you have the mass as a function of time times the acceleration, which is also a derivative of velocity. Um, yeah, so yeah, this part is like a function of how velocity changes with the mass decreasing. Yeah, big improvement. I actually have kind of figured out. I might not. I don't think I'll still get like all points, but I gave it a shot. I learned a lot. All right, for this next one, I think I got like most of it. I just like ran out of time for it, and I also kind of like figured out a better way. So yeah, first I just started out by like writing like the extended Bernoulli equation right here, and then I realized that since there's head loss, the energy Bernoulli equation can like work pretty well for this. We just have to like cross out some stuff. So with this large tank being supplied to a rooftop, this like initial point, the tank, there's not going to be any velocity there. Oh goodness, is my pen is just like not working suddenly. I need to switch out the battery. Yeah, intermission. Go. Yeah, and hopefully this isn't being counted in my explanation. You can just like fast forward if you want. There we go. Yeah, this thing is really old, so sorry about that. But yeah, you can cross out the velocity for that because it's just gonna be like 0 on the surface. Um, height is just a reference point, it's gonna be 0. No pump, no turbine. Um, A is just assuming 1, so we can just like cross those out because nothing is specified. Um, yeah, and then once we have that, we can rearrange the equation to just this. And we are finding the second velocity again. So, yeah, because we need to find the discharge rate, which is cubic meters per minute, which we can just like multiply by the diameter of the pipe. But yeah, the energy Bernoulli equation is good for that. yeah, rearrange so that velocity is one side and all the other stuff is on the other side. And yeah, you can isolate it completely and then plug it in. And for velocity, we want to get I kind of like follow the units for this. We want to get a unit of like meters per second. So for this little part right here, you're going to get everything in meters once you like cancel everything out, and then these are also meters, so you're allowed to subtract them. And then yeah, multiplying by gravity times 2, you're going to get 361.12 meters squared over second squared, which when you square root that, you are going to get meters per second. So you got your velocity. Yay. Then you can multiply that by the cross-sectional area of the pipe, which I think is like 5 centimeters? Yeah, it was 5 centimeters inner diameter. So yeah, just multiply that. And then, yeah, the answer was in cubic meters per minute. Otherwise, it's going to be like bitty per second. So it's 2.239. Yeah, I actually got an answer for that. So nice. Yeah, so this one was like a hot mess on my original test. Um yeah, I was just freaking myself out for it. But yeah, let's just go to the right thing. Um and then we'll like see what I did wrong. So yeah, using Archimedes' law, the buoyant force is going to equal the weight of the water displaced, which is also equal to weight of rocks, like in the water. Um, so for the mass of the water, you can do like the density of water times like the amount of the box submerged, which is like volume. Um, so you get 1,000 kilograms per cubic meter times that volume, and then it ends up being 260 kilograms. So you can find, yeah, with like that weight of water displaced, it's going to be equal to the weight of like the total weight of the box, according to Archimedes' law. And then, um, yeah, then for finding the density, we know that the mass of the box is going to be equal to the, sorry, weight of the box. Weight of the box is going to be equal to the weight of the water. So you can just like you cross out gravity here because they're the same, and rearrange it so that like you get like the total box volume. And since it's like 260 kilograms and it's 1 cubic meter, then you can just know that's going to be 260 kilograms per cubic meter. So it's about like a quarter of the density of water. Yeah. So you could do a similar thing with using force balance and hydrostatics. So the gravity force is going to be equal to the mass of the box times gravity, which is equal to the density times the volume times the gravity of the box. Yeah, and then the gravity force is going to be equal to the buoyant force. So, um, and buoyant force is just like density of water times the amount of rocks that's submerged in gravity. So yeah, we already have like 3 parts of this equation. You can just rearrange, which I originally did that. I believe like kind of over here. That's why I was like aiming towards. Yeah, really over here. I just like I don't know what I was doing. It was bad. Um, but yeah, you get the same answer, which is great. We want that. But yeah, I just like I had like I did I had the wrong idea with like what I wanted to do with it. And yeah, just panicked. This one I got completely correct. Here's the original. This one I think I got like mostly correct. There were some glaring mistakes like right here. This is 4 times smaller than it needs to be. Because look at that. That's literally like the diameter, and I'm treating it as a radius. That's bad. So I didn't do that on the right one. But I kind of approached this problem the same way. Um, but yeah, I also didn't have like the right like mass balance momentum balance equation. But yeah, so I got the right velocity check this time. Um, for the velocity of the nozzle or like the tangential velocity for the sprinkler. I did get that right originally, so that's great. Yeah, so I didn't write like my entire angular momentum balance, but I did like you get like this equation off of this equation, which can then be which can be rearranged to like this part going out minus that in plus the torque equals 0. So that's how you like get to the torque equation. And also for this, we're assuming like beta is 1 because nothing else is specified. But yeah, you can get to the torque equation of 2 times, because there's 2 nozzles, over times the mass flow rate. But you want to divide that by 2 because there's 2 nozzles, so that like original amount of 23 kilograms per second is being split. But those two cancel out. So yeah, then beta times the radius, which is going to be just like 75 centimeters, like half of the entire thing. And then the VA jet minus V nozzle, which is like the velocity of the water spraying out the jet minus like the tangential velocity of the nozzle like spinning around. And that will get you your torque. Yeah, multiply that out, you get 152.25 Newton meters, and for Newton meters, units, I also follow this, it are kilograms times meters squared over seconds squared. So, and we get that. I just like immediately converted it. And then, yeah, if you wanted to generate more power from this system, you would actually want to decrease the rotations per minute, which is a little bit like weird. But power is calculated through the equation, like angular velocity, like omega, um, times the torque. So you would think it really makes sense to increase the RPM, because like if you increase omega, it's gonna get bigger. But the thing is with torque, um, it's going to be factoring in the tangential velocity, and tangential velocity is calculated by this. So the lower the tangential velocity, or the velocity of the nozzle, the higher the torque is going to be. So if you increase that, there's actually going to be a point where, like, if you increase omega, you're going to get to a point where V jet equals V nozzle, and then torque is going to get 0, and you're going to get 0 power. You don't want that. So, I didn't actually calculate the exact number that the ideal RPM would be, but there's an optimal point that is like less than the 280, where there's like maximum torque, but still like a big enough omega to like get a good power. So yeah, but yeah, if you decrease it like too much, it is going to start like going. The power will start to go down too much. It's kind of like a parabolic equation, and there's going to be like diapex there. Yeah, hopefully, yeah, that's everything, I think. So, yeah, thank you for watching this. Let's see if I can, like, edit this out. So that recording should be set up. I'm just gonna move this. Yeah, I'll just do that.